Okay, hello everyone. I'm He Wang from Peking University. It's my pleasure to share our recent progress on learning universal dexterous and grasping policy from 3D cloud observations here. And so I'm pretty much, my background is pretty much some vision plus some robotics. So as the first speaker in this workshop, our topic would be a little bit robotics. So I would start with, talking about hands from a robotic dexterous grasping perspective. So everyone here is interested in dexterous hand, right? So I think like why dexterous hand is so important because it can do a lot of interactions. Arguably, grasping is usually the first step towards general interactions. That's why we want to study grasping in both vision and the robotics community. In recent year, there has been a lot of progress in devising algorithms for parallel breakers. However, parallel breakers only have 7 degrees of freedoms. Compared to it, Dexter's hand provide you much more degree of freedoms and can support complex manipulation. That's why this is, at least from my opinion, this is the future of a more general interactive paradigm in robots. So today, I will first review the state of grasping object grasping in parallel breakers. So this work on the left, it is a data set called DexGraspNet 1 billion from Shanghai Jiao Tong University. On the right is their learned universal grasping work for parallel breakers. So this data set comprised of like a 1 million labeled 7 degree of freedom grasping posts on real world scenes. And based on this, they take point clouds as input. They are able to learn a very generalizable grasping algorithms that predict accurate grasping poses on arbitrary objects as shown on the right side. This is what have been achieved for parallel breakers. However, for Dexter's hand, 6 years ago, 5 years ago, we already see that OpenAI has this amazing work. They use robotic dexterous hand to manipulate objects, reorient it. However, this is just a known instance. We know that here they do not estimate the pose of the hand. Instead, they directly use a policy to output the action, the manipulation actions. So this policy is actually learned via reinforcement learning in simulator. Arguably, policy give you more freedom of manipulation than first predicting pose and then using motion planning, especially for Dexter's hand, which has very large degree of freedoms. However, this work also has several limitations. First, it only can be only used on this this single instance, and it
Okay, and then Change to the display.
Okay, so and also again, like in Dexter's manipulation case, we want this Dexter's grasping to be a policy instead of a two-stage thing. First, with predicting object pose or grasping pose, then just do motion planning, because this motion planning things probably is not the general thing for manipulation, especially for Dexter's hand. So this is basically our desired feature: very high generalizability, vision-based, and learn a policy. And this thing is very challenging, I have to say. First of all, if you guys are familiar with reinforcement learning, you would know that the policy gradient in RL is very noisy. Due to this fact, if you directly end-to-end learn a vision-based policy, then with very high chance, the noisy gradient would ruin your vision backbone, which yield, zero performance on grasping success. And another thing is generalization in reinforcement learning is also very challenging. If you want your algorithms to work for a single instance in a specific pose, it is okay. But if you want your policy to work on arbitrary objects with arbitrary object poses, it will be really hard. Let me give you guys an illustration. So basically, let's start with state-based policy. So if this policy can access Oracle inputs, basically composed of object poses, object velocities, everything, then for a single object with fixed initial pose, training using SOTA on-policy reinforcement learning algorithm, for example, PPO will give you 97% of success rate, which means it is easy. However, if you just randomize the initial pose of this object, then the success rate will sharply drop to 15%. So if you increase one object to 10 objects, so you need to learn a policy that works for 10 objects with fixed initial pose, then the success rate dropped from 97% to 36%. Finally, if you want to train a reinforcement learning algorithms on 10 objects with random initial pose, then the success rate is 0. So which means if you want the reinforcement learning algorithms to work on a generalizable case with a random initial pose, then it would be very, very hard. So although this is, and this case is already a simplified case because you can, the algorithm can access the Oracle input, which includes the object pose, object velocity, etc. If you only allow vision input to the policy, then the success rate would be 0, even for a single object with fixed initial pose training from scratch. So this basically illustrates how hard it is to learn a generalizable vision-based policy for Dexter's object grasping. Definitely behind this, a lot of challenges come from the high dimensional action space of Dexter's hand. And a Dexter's hand can have 24 to 30 degrees of freedom for like shadow hand. This is known to be a very challenging reinforcement learning problem due to the high action dimension and the curves of dimensionality in reinforcement learning. So that's why we may think, can we provide more demonstrations to warm up this reinforcement learning problem? So if we want a lot of object grasping demonstrations, we need a lot of Dexter's grasping data. Currently, people have to have used synthesis method to create a dexterous hand grasping data set. This include object OBMan, HO3D, DexYCB, etc. Some of them are based on manual, which is human hand, and only a single word DDG data is for shadow hand. However, if you look at how many object and category do they have, how many grasping do they have in total, they are not in a large scale. So that's why even if you want to provide some demonstrations to dexterous hand grasping policy learning, it would be a big problem. So that's why in this talk, I would cover our recent works from both data and algorithm perspective. At the very beginning, I would introduce our DexGraspNet, which won the ICRA 2023 Outstanding Manipulation Paper finalist. And this work synthesized large-scale dexterous grasping data set so that we can have some guidance to the policy learning. And then UniDexGrasp, the first version published in CVPR 2023, and our recent version, UniDexGrasp++, published in ICCV, this year's ICCV as an oral. So I would start with creating a large-scale dexterous hand data set. I believe this would be interesting for both vision and robotic people. And so this work is called DexGraspNet, large-scale robotic dexterous grasp dataset for general objects based on simulation. So as what I shown before, the previous hand dataset are not in a large scale, especially for robotic hand. For example, shadow hand. So in this work, we create a large-scale data set with 1.32 million object grasping that covers more than 5,000 objects. And for each object, there are at least 200 of objects. And this data set so we differ from GraspIt, which is a very old school grasping synthesis method that simply synthesize grasp by clenching fingers. And it will yield very low diversity due to this naive search policy. And so it's not really like our human. And our work is based on a differentiable force closure estimator published in RAL 2021, and it can support very high diversity. However, the yield is very low. It takes a very long time to generate one specific dexterous grasping pose. So that's why in this work, our emphasis is to maintain high grasping diversity while significantly improving the efficiency and the robustness of this dexterous hand synthesis method. So the pipeline of this work can be divided into 3 phases: mesh pre-processing, grasp generation, and grasp validation. So to collect as many objects as possible, we found that the mesh quality is very important for the synthesis algorithm. So we fixed the bad mesh with manifold plus and normalize them into suitable scales. We apply the new is the convex decomposition algorithms that's called COACD to decompose them for physics simulation. The synthesis task is formulated into an optimization problem. A grasp is parameterized as a tuple. We want to synthesize stable graphs by optimizing 5 energy terms. The core design is the force closure energy, which guides the generation to yield physically stable grasping. Basically, all the generated dexterous grasping poses can give you a force closure grasping that can like support acceleration along arbitrary directions. And all the other terms are some direct penalization, for example, surface collision, penetration, etc. So we found that a mixed annealing and gradient descent strategy is enough for this optimization. The grasp tuple is updated using gradient descent and accepted within an annealing rule. The loop is repeated 6,000 times until the energy converges. We visualize some trajectory of this visual optimization process. So starting with an initial grasping pose, this hand finally reaches a physically stable grasping pose. And this process is significantly speed up by our algorithms. So after we generate the grasping poses, we need to verify whether this grasping pose can grasp this object stably. So we put those generated grasping pose into ASIC gym simulator. We squeeze the fingers along the normal of the contact points to obtain the target pose, which is used for position control. A grasping is considered successful if it resists under 6 axis aligned directions and holds a penetration depth of less than 1 millimeter. So we do a lot of work on the efficiency and the robustness of the second stage. We carefully fine-tune the optimization algorithms and improve state initialization, making it converge faster. We also choose alternative penetration energy to make it more robust to collect more objects. We customize CUDA kernels from NVIDIA API to accelerate the bottlenecks. So in total, we achieve more than 50 times acceleration than the baseline method. And this is the qualitative results. So we generated about 200 valid grasps for each object with shadow hand. Among one category, there are at average 40 objects instances. The entire data set consists of 133 object categories. We collected more than 5,000 objects in total and generated 1.32 million valid grasps, making it the largest dexterous grasp data set, 2 orders of magnitude larger than the existing works. And here is a comparison of our results with those from GraspIt. So basically, all the blue ones are from our method, and the red one is from GraspIt. You can see that grasping generated by GraspIt twist their fingers and looks very unnatural. And our grasp looks like contain very high diversity and remaining very natural. And also with simple modification, this entire pipeline can be applied to other dexterous hands, such as human hand, manual, and Allegro robotic hand that's only with 4 fingers. We provide the full implementation of them in our GitHub repo, so you can use it. And we can also customize for objects on the floor so that the generated grasping won't penetrate the floor. Okay. So if you look at our benchmarking result, then we will see that the learning-based synthesis method achieve higher quality and diversity when they are trained under our data set. However, none of the existing methods can perform really well on both quality and diversity. Basically, this data set provides new challenges to grasping pose estimation community. So this is basically the project page and code for this project. Please visit it to access code and customize for your use. And the one limitation of this work is that it only care about force closure grasping. So our very recent work, task-oriented Dexterous grasp synthesis work provide you a new tool called differentiable grasp range boundary estimator. It can support grasp synthesis of non-force closure grasping. For example, the grasping can only resist a torque along one direction or a force along one direction. For example, how to rotate this knob. You need like this grasping not necessarily to be grasp force closure, but only need to give you the torque to rotate this knob. And for example, to turn this handle. So yeah, please search this work on the archive to look into more details. Then I will switch to the policy learning part of this talk. So, so based on our DexGraspNet data in CVPR 2023, we proposed the UniDexGrasp. That is the first universal robotic Dex grasping policy learning works that can generalize across 5,000 objects with arbitrary poses. And so in this work, I will only give you a very short overview of this work. So in this work, we will split the grasping pose, grasping into two stages. In the first stage, given the point cloud of this object, we would first generate a lot of grasping poses using a flow-based neural network. And this flow-based neural network is basically a conditional generative model that gives you a lot of valid grasping poses. And then you can select one grasping poses as the goal. In the second stage, we would use the goal conditioned Dexterous grasping policy to follow the grasping goal and grasp this object and lift it up. So here we show some qualitative results, and for different objects, our first stage can generate valid grasping poses supervised learned from DexGraspNet. And then based on this desired grasping pose, our generalizable goal conditioned policy can execute this grasping. Well, what is more interesting is that we can use clip feature to select desired grasp among many generated grasping poses in the first stage. For example, we can describe our desired grasping poses like grasp a bottle by the body, by the bottleneck, or from below, and then the clip feature will select the grasping pose that satisfy your description, and then you can use our generalizable goal conditioned policy to execute this grasping. I think in this work, we mainly explore two things. The first thing is how to make this vision-based generalizable policy learning work. So the idea is inspired by the previous generalizable policy learning work. Basically, we first need to learn a state-based policy, and then you can distill this state-based policy to a vision-based policy. The state-based policy can access oracle information, for example, object pose, object velocity, etc. However, during distillation, the vision-based policy no longer take inputs of those oracle states. Instead, it can only take inputs point cloud. So this is the way how you can avoid, end-to-end policy learning to ruin your vision backbone. And so the problem becomes how to learn a very successful state-based policy. So we have two tricks. The first trick is we build a canonical reference frame in the hand space, so that all the objects are under this hand space to consider is point cloud, which significantly simplify the observation space. And then we also propose an object curriculum. So basically, Basically, we will first learn this grasping policy on a single object. I already show you guys this will give you 97% of success rate. And then after that, we will increase the object set to be 10 objects that share the same object category with these objects. Then just fine-tune this policy on the 10 object set. We find this will still maintain a high success rate. Finally, we will gradually enlarge the object set to be 5,000 objects. This object curriculum learning significantly improved the grasping success rate. At the end, we achieve about 70% on whole 5,000 objects. So in this year's ICCV oral UniDexGrasp++, we want to further push the boundary of this generalizable object grasping policy learning. So we propose this work, UniDexGrasp++, improving Dexterous grasping policy learning via geometry-aware curriculum and iterative generalist specialist learning. So compare between UniDexGrasp and UniDexGrasp++, we see that we have in general about 8 to 10% success rate improvement on both state-based or vision-based settings on both train and test set. So the idea in this UniDexGrasp++ is that we want to form several specialists that only take care of a very narrow distribution in the object distribution, and they will learn their separate policy and then distill to a generalist that take care of all the objects. This process can be done hierarchically. First, many clusters, and then distill to, for example, 0.1 times the total number of clusters, and hierarchically distill to, at the end, one policy. So this is inspired from several previous work, including this work from Professor Hao Su's lab, and also work from Sergey Levin. I will skip the detail. Also the divide and the conquer RL from Professor Sergey Levin's lab. So in this work, we try to handle this universal large-scale Dexterous kind object grasping of various categories, especially from released visual signal as input. So we already talked about that directly learning a vision-based policy will result in low performance and generalizability. So in this work, we'll also start with a state-based policy and then distill to a vision-based policy. But what is different is that we will handle this generalizable policy learning through partitioning the task space into a lot of subspace, and then learn specialized specialist for each sub-task space and hierarchically distill back to a single policy. So the main pipeline of this method is definitely first to learn a state-based policy. And this can be divided into several parts. We first train a state-based policy for like an object level. And then we will distill to larger clusters that comprised of several objects. But now the problem is, how do you divide this task space? Depend on which rule you partition the whole task space. So that's why we call this work geometry-aware curriculum. So we will train an autoencoder to do the reconstruction. And in the feature space, we will form many clusters in the embedding space of this autoencoder. So we will use clustering algorithms to form a lot of geometrically similar clusters. Note that not one object with different poses will be put into different clusters. Only objects with similar shape and with similar pose will be put into one small clusters. And after a specialist learn on this small cluster, it will distill to larger clusters. And this larger cluster will be again used the reinforcement learning to fine-tune it to improve the general success rate on this larger clusters. And this is a visualization of our clusters. So if you have category level clusters, then they are basically objects from same object category. However, they may have different shapes. If you have state-based clusters, this is again, those objects are from similar object categories and from similar poses. If you have vision-based clusters, those objects will even with similar grasping poses. This is basically illustrate why our geometric clustering algorithms is aware of the object grasping learning and also forms very specific narrow distribution that significantly simplify the policy learning problem from scratch. And after learning the state-based policy, we can distill it to vision-based policy. And this distillation can also happen from clusters to very generalizable generalist. Very similar to what we have done in state-based. So I will quickly show you how this algorithms performs. So at the very beginning, our specialist will have our specialist will have 86.8 success rate. After it distilled to generalist, it the performance drops to 84.4. And if you further do the reinforcement learning, it will improve to 89.9, and after distillation, it will drop to 87.9, and then you can do reinforcement again to improve it to 90-ish. Okay. So this is what happens after distill to vision, and at the end, we achieve 85.4 success rate based on vision input. So this is qualitative results of our Dexterous grasping policy after it's learned on 5,000 objects. It can successfully grasp objects and yield more than 80% success rate. This is, to my best of knowledge, the most successful generalizable universal Dexterous object grasping algorithms. So to summarize, so we basically, in this talk, we cover our data effort and our universal policy learning effort. There are still a lot of limitations, especially regarding sim to real. We hope we can improve on those fronts in the future. Thank you very much. And this is my email and homepage.